everybody. Summertime in Automotive is the title of our talk. In the next 30 minutes, we are going to walk you through our purely Rust-based implementation of a SommIP stack. We will try to highlight some of the challenges we were facing when doing a SommIP stack in Rust. Speaking of we, so who are we? I have Simon, a lovely software developer from Accenture, and Morten, also from Accenture, who massively contributed to SommR. And of course, me, Sebastian, or Sebs, I respond to both. Introduction to SommIP. So, how many of you heard of SommIP? Okay, those are the automotive dudes. So for the rest, I give you a short introduction. So SommIP is scalable, service-oriented middleware over IP. The standard basically defines the remote procedure calls and how the protocol is working, and the serialization of the payload. SommIP is actually two protocol standards in the trench code. We also have SD, which is the service discovery protocol. And SD is used for discovering services, who would have thought that, and for publish-subscribe communication patterns. It is used in the automotive field in rich OS ECUs, which are more like Unix or Linux-based ECUs, and of course in real-time embedded operating systems. SommIP itself can be sent via TCP or UDP, and what wouldn't be a good protocol introduction slide without having those crazy tables showing how the protocol looks like. So we have some kind of like message ID, which consists of a service ID and a method ID, a length, some sort of session handling, a bunch of flags, and the payload, which is serialized according to the SommIP serialization. When it comes to payload serialization, we distinguish two different types of serialization. SommIP, the standard defines like length value serialization, and tag length value serialization. The other part of SommIP is service discovery, and service discovery is only transmitted via UDP. As you can see, it is quite similar to the SommIP frame itself, so yay, you only need to write one codec to decode it, but then you need different handling because in the end it's a different message. In a discovery scenario, we speak of providers and consumers, provider and consumer services. Providers send offer service messages following the message format I depicted just briefly, and consumers send find service messages. And with no time to lose, I hand over to Morten for the serialization.
Question mark? Ah, okay. So let's see about serializing some SommIP payloads. So when talking about the payloads, one thing that we have to keep in mind is that unlike for the header, we don't just have one format that will fit everything. We will have lots of different SommIP services defined, and so each and every one of them will be sending different data to each other and also different types. So what we come up with has to work for a lot of different types. And if you want to serialize types in Rust, then usually you end up using xerdi, and that's also what we ended up with. So our basic idea was, hey, let's just implement a serializer, deserializer for xerdi called xerdi SommIP. Now, this immediately caused two challenges. The first one is that xerdi itself does not provide enough information for us to actually serialize the payloads. So I have an example struct here. Yeah, you can see it derives deserialize and serialize as usual. But you can see for both fields, as seen by the comments, they are missing the ID. So as Zeps said, you can have a tag length value encoding, and for that you need to have an integer ID for every field, which we don't have here. And further, for vectors or in general collections of data, because SommIP can also work with real-time operating system or other embedded ECUs where you need to know your memory usage beforehand, you need to know what the maximum length of this vector is going to be. And on top of that, yeah, you also need to encode this length somehow, and SommIP gives you different options of how to encode it, and you have to pick one every single time you use a vector somewhere. So all of this information needs to be added in some way. But that's not yet the biggest challenge. The bigger challenge is that depending on how you use a type, it might get serialized differently. Yeah, to maybe better understand this, I have an example here. You can see on the left we have a struct called example, which simply has a vector inside. And then on the right we have two structs foo and bar. Both of them use or have a field of this example type, but both of them also have a comment that one of them wants to use length fields as U8 and the other one wants them as U16. And SommIP will actually honor this request. And so you can see here in the schematic display of the serialized form that the length field on the left side, yeah, we have a foo, we have the vec inside, and then it starts with a U8 length. But on the right-hand side, yeah, we have a bar with the vec inside, and it starts with a U16 length field. What that basically means is that by the time we are serializing the example over here on the left, we need to know if we came from foo or from bar. Otherwise, we don't know what the exact length field is. And so combining all of this, yeah, when I'm trying to figure out how to serialize a given SommIP payload, I end up looking like this. Okay, so how can we approach this? Since we need to add more information add information that is not usually there, so our first approach is, or our approach is to use a proc macro once again. We already heard proc macros a couple of times here during the Oxidize. And what we will do is we will define later on our own trait that has all the information, and we will use a derive macro to generate this trait implementation. And then this allows us to use these nice attributes from Rust to simply add all of the information inline into the code, as you can see here. So now we are done with serialization. Serialization, right? Well, no, we have now the information in our source code, but we need to get it actually to the serializer. And here we have, again, a small problem, because our serializer is a Zerdy serializer, so it has to implement this trait from Zerdy. And what you can see here, one of the problems is, Zerdy at some point will ask us to serialize some value t, and the only thing we know about it is that it implements serialize. So we don't have access to all of the extra information that we just added. Now, quick side note here, it would be really nice if you could write something like this in Rust, some kind of associated trait. Then you could say, okay, there is some associated trait, and this serialized X trait, it just shows up in all of the where clauses. And this way, the type system could then ensure that we always have access to all of the information we need. But as you can see, based on the missing highlighting, this is not currently valid Rust code. So we have to come up with some alternative solution. Thankfully, the one thing that we do control is the entry point to serialization. So if you've used Zerd.json, then you know that there is some toString method, you give it your type and you get the string out. This is here exactly the same for SommIP, but we just get a vec U8 out because it's a binary protocol. And because this is defined by our crate, we can add whatever we want in the where clauses. And so we have here SommIP available. Now, what is left is designing the SommIP trait. And the SommIP trait has to fulfill, or has to achieve two things. First off, because we only have it at the very top level type, it needs to include the information not just for its own type, but also for all types used by that type. So if you have a struct that has 5 fields, we need to know the type information for all 5 of those fields. And the second point is that our trait has to be efficient, because we don't want to end up spending God knows how many CPU cycles on figuring out how to serialize the messages. So it has to be efficient. So now let's take a look at the actual trait. This is really the complete trait. I didn't leave anything out. I just removed some doc comments. And one thing you can see here is that one design principle here is you can see we don't have any functions or something like that in the trait. We just have a associated const in there. And this forces anyone who is implementing this trait to put something there that the compiler can generate at compile time. So we are avoiding runtime overheads here by using const. So what is this SommIP type that we have there over there? That's just a simple enum. This is not too interesting. Yeah, just an enum over all the different possibilities that we have for SommIP. Let's take a closer look at the struct variant, because that is honestly the most complicated one. But again, you will find there is nothing too surprising here. Yeah? Struct has a name, bunch of fields, and then every field also has a name, an optional ID, because as Sebastian said, you can have length value or tag length value encoding, and you only need the IDs for the tag length value. And then you have the actual field type. And what you can also see here is two things. Yeah? First off, you can see that all of our references here are static. This is, again, to force you to use something that can be done at compile time by the compiler. And it, of course, has the nice benefit that we don't have to deal with lifetime bounds in our code. The second thing you note is that the fields array is just a slice in this case, not a vector or not a hash map or something like that. And that is, again, due to the fact that we need something that can be done at compile time, and vectors or hash maps cannot be instantiated at compile time. So now, combining all of this, let's go back to our example from the first slide. And this, in the end, I hope you can read it, is what the SommIP proc macro will generate for the implementation. Again, you can see that there is nothing too surprising here. So we have the type is obviously a struct. Then we have the name of the struct in there, and for the fields we have an inline array, because that is something that the compiler can instantiate at compile time. And then for every field, again, the same thing as we had previously, the name, the ID. And then for the field type, you can see here, it just references the SommIP implementation of that other type. So here we can link the different types together and ensure that all of them implement SommIP. Now, one final thing to note here is that for the vector, we can't just reference the SommIP implementation of the vector, well, because every vector that you might use somewhere in your code will be slightly different. It will have a different max length, different length field size encoding options. And so the proc macro has to be a bit smarter and regenerate this information every single time a vec is used somewhere. That's it already about serialization. If you take all of this, add it together, add a whole bunch more code that I didn't have time to get into, then you end up with something that can actually serialize SommIP payloads. And with that, I give over to my colleague Simon for some I/O.
All right. Thank you a lot, Morten, for walking us through the serialization. So now we want to talk about the I/O in our application. For this, I brought you a small schematic overview. Imagine for SommIP, we have a lot of applications, and they want to consume services, provide other services, and in the end, that means they need to send messages through TCP or UDP sockets or receive on them, or even listen on them. So TCP sockets can be connected to, or they can be listening, so server or client. As you can see in these schematic, some of those sockets may be actually the exact same. So they're on the same address, same port. You could wonder, wait a second, does that actually happen that often? It does, and by design. Those of you who know SommIP and work in automotive probably also know we have a lot of really small ECUs that can barely handle one connection with their resource constraints. So that's why intentionally they put a lot of services and a lot of messages on exactly one connection. This opens a lot of room for us to reuse this fact. So what we essentially want to build is a proxy that allows other applications to consume or provide services without handling all the complexities of SommIP. And this will come down to an N-to-M mapping of connections. So it's kind of a network proxy, the I/O part, if you will. We could have used something existing, but we wrote this part ourselves to have fine-grained control and also to save some overhead for bells and whistles that we don't need in our example. Here is another schematic. We will later look at this again, but just to give a very rough overview. We have still the applications on the left side, and we have now the TCP and UDP sockets grouped together. So you can imagine, okay, there's several of them that go together and that will be shared. And in the in the middle, we have the big daemon block. Let's ignore for a second the service discovery. This is part of it as well, but we won't have time to go into this. Morten could give, I think, an hour talk on discovery itself. But what is important for us now is that per app, we have one handle of the core. The core does things, high-level SommIP things like consumer service, provider service. And we have a handle for I/O, which will take care of, okay, I need to connect before I actually send a message. Or because I'm subscribing to a service, I need to start a listener on something, when I provide a service. And another important thing, you see this one I/O impl block. We have one central part of our module where all the instructions to open connections come in, and we handle all the connections on the right. We'll look into this more detail now, but this is important to know. Several apps go on a lot of handles, but they come down to one backend, we may call it, that serves it. So I hope you can read it. Challenges that we had to overcome. I want to walk you through 3 or 4 of them. So one is I/O operations should not block each other. Imagine a very slow TCP connect over the network. It takes a while until the other side answers. Yesterday we had a lot of talks. I remember, Andy, from your talk saying parallelism and async is really hard. I also remember, Steve, you saying in the keynote, yeah, async is like, it feels like it is treachery. It breaks all those guarantees that Rust gave us in the first place. But guess what? We're doing a lot of network I/O and we want to do it as efficient as possible. Async I/O it is. So we are using async I/O primitives in a lot of places. There are still things that you can do wrong. You can still accidentally do something blocking in your setup, so you have to really watch out. One example I want to give you is, okay, let's take TCP and UDP sockets. We open them, in our case we use the Tokyo executor, so we use the Tokyo types of TCP socket and UDP socket. However, what do we do if the Tokyo API doesn't expose all the options that we need on a socket? One example is the Tokyo API, as of now, does not expose the set reuse address flag for UDP sockets. But we need that in our example. So what we can do is we can open the socket with here socket 2. We could also use a different library, and we can set all the normal or even esoteric flags that we need with NIX, with libc if we don't mind the unsafe, and then just turn it into a Tokyo type. This is a great thing that from the conversions this is possible. Just keep in mind we have to set the non-blocking flag definitely. If we don't set it, we are violating the contract and we will block the executor pretty soon, and notice that. Okay, another thing so that we do not block on different operations is that we spawn one task per connection. Yesterday someone mentioned intra-task and inter-task concurrency. So what we're doing here, okay, we do a little bit of both, but we are heavy on the inter-task concurrency, I would say. So one connection is one Tokyo task, and every listener is one Tokyo task. We spawn them in an actor pattern. Maybe a quick show of hands who knows about actor pattern? Okay, great, thanks. Then we don't need to go into the detail, and I hope no one grills me for being somewhat liberal with the expression. So just an example, when we want to have a new connection, we will create a channel so that we can communicate with it as the inbox of an actor. Then we will insert this connection into a map where we can look up the next time if we already have this connection for others, and we could forward interest of another party. And then we spawn it into a join set. I think Andy or someone yesterday had a join set already in their presentation. And from the join set, we can also pull out their tasks and see what happened there. The cool thing is there's no lock contention or deadlocks that we would have if we would use a mutex here. It would be ugly to, I'm not sure if it's even that possible in all cases to do this with a lock, because we need to await on something that would be behind the lock. On the flip side, we are accepting that there is the risk for race conditions. So there can be things going wrong, and we'll look into 2 examples of this later. As in actor patterns, often we propagate results back with one-shot channels. So you say, I want to connect, and if the connect works, then at some point, like this result channel gets passed to the task does the connection, and if everything works, you get OK back. If something goes wrong, you get an error back, and crucially, if your result channel and your sender is dropped on the way because something terribly goes wrong, you also notice, because you will not get the answer, you'll get the channel closed. So that's quite important for us. Another thing, we need to think about back pressure. Again, just asking, I guess, who understands back pressure in this context? Okay, a little less than the actor pattern, so let's just shortly say, if a consumer on one end of the channel can't keep up as fast with what is pushed in as the one that's providing messages, that will back pressure in the sense that the one providing will be blocked from continuing its work. And so in all this application where we glue everything together with channels, we need to really watch out where this can happen and really think about what will we do? Could this take longer? Could this not take longer? Do we need a timeout somewhere? And we made a big sketch together at some point and said like, okay, this is all the channels, this is how they're glued together. Where do we need to watch out for it? Okay, how do we establish an order when 2 clients try to connect at the same time? Let's remember our chart from the architecture. The good thing is we have one application backend. So there's one backend that serves all the requests, and that means there will be a sequential order established through this one channel pulling out data. You can imagine it a little like this. Sorry for the broken formatting. There's a main loop running in this impl block that will get all the instructions, connect, listen, and so on, dispatch them. And so it holds all the maps and so on that keep track of which connections are open, which are dead. We still have to watch out for race conditions that we have due to independent tasks. So listener and connection task run independently intentionally, so we need to watch out for that. Imagine things like a task exited, but we haven't pulled it out of the join set, so we don't know about it. Or a connection task is about to close because there's no interest any longer, but then there's listener still in the queue. There's even more. You drop a socket and you think you can reuse it right away, but your operating system says address in use and TCP linger settings and more things. So there's a lot of things that still can go wrong where we had to walk through individually. One last thing I want to share with you that I also really like about our architecture, and I must admit, I didn't come up with this. I kind of copied that from ideas from Sebastian and Morgen because they were used in the core and in the SD, so in the service discovery. We clean up connections by using cancellation tokens. Who has used cancellation tokens? Yeah, not that many people. It's a great thing. So we use the ones from Tokyo Util Sync. They allow you to spawn a token where you can wait in blocking or in async way whether a task is done. And you can cancel them from one place. You can say this is done, and then everywhere where you showed an interest, I want to know when this is done, you get the notification. Even better thing is we can turn them into drop guards. And we all know in Rust from other things, we love stuff that happens on drop because then we can't forget it. So that means in the connections and listener tasks, we just await and when they're done. So here's an example. We connect to an endpoint. You see a token that we create. We turn the token into a drop guard. We pass the token to the connection, like when we do connect, and then we store the guard. We also store the token because we might need it at another point, and you can't turn the drop guard into a token without disarming it. That's a different story, but yeah. So in the end, in the task, we just wait until we're done, and it's like reference counting almost, where you say, okay, as soon as all the interest is done and the input queue is empty, we can exit the task. Okay, and with this, I hand over to Sebastian for testing.
Thank you. Oh, sorry. I need to speed up a little bit. Testing. So, all you know, like these neat test environment we get with Rust. And this is pretty much it. Test SommR, all is good, we're ready. Well, not seriously. So in detail, in SommR, we have a slightly more complex system. Of course, we have our unit tests, let's call them that way, but we have a daemon that is a separate process. We have our protocol, and we have our internal protocol, and we have the SommIP protocol that we talk to and network to. So what are the challenges here? Well, we kind of wanted to have like an end-to-end testing here, so like protocol, daemon, and of course the SommIP if we work according to the protocol specification. We wanted to inject errors into the protocol to see how resilient our daemon is if someone uses our protocol wrong. We wanted to have like an automated network set up in the background somehow. It should be fairly simple to use. Of course, it must run in a CI. And if you're heading towards mass production approval, you need to face the quality department later on. So what was our first approach? Well, scripting, scripting, and even more scripting. We ended up with like a lot of lines in Bash and Python, and you can imagine like our test coverage did not went well. If you approach your quality department with such a coverage, well, this is what's going to happen to you. What was the second approach? Well, provide a test macro. So that means we turn something like this into something like that. So, but how are we going to do that? Well, once again, we love it, proc macros to the rescue. Sadly, proc macros are a super wide field, and you can have a complete presentation of its own talking just about proc macros. So I will just walk you through some things I found interesting. Sorry for that. Parameter sanitation. So since you can do whatever you want in the proc macro and in an attributed macro, you can even write non-valid Rust syntax. You need to provide, or you need to take care of like sanitizing what you get from a user. Here I have a simple example how we do the sanitation of the incoming parameters. I can just stress is like give back spanned errors wherever you can because your user will see where he does something wrong. I can also stress that it's like must be a literal is not a good error message. Furthermore, if you spawn processes like we do when we spawn our SommR process in the background, make sure that you copy the I/O from your spawn process to your parent process because you won't get locks from your child process. Also, what is really important, and I found myself like really puzzled for a while, is like set up a custom panic hook that cleans the child process. So once it exits for good. So once something panics, it exits for good. The closing words here. Write a small, create a small project next to your macro for testing and debugging. Cargo expand the hell out of your macro because cargo expand is the only thing you have. You cannot debug it. Quote and syn are your helpers. Use it. Don't try to figure out how token stream works on your own. It's too time consuming. Use tribal to sanitize your error messages. And in the end, your test coverage will look like this. And actually, it looked like this once we had the macro in place. People start writing tests, even myself. So, and then you can approach your quality department. They will be happy. And we're actually close to like 80% coverage right now. Yay. The end. Thank you.
Nice finish line rush there on the timing. Let's take one question. Ooh, I'm going to go here. And we do have the lunch break, and there's 3 of them, so they can divide and conquer in an hour.
Approach
so,
us.
but we'll do 2 questions. It's fine.
All right. Hi. I had a question to deserialization and serialization. From your slides, it looks as if it's done eagerly, so whatever's on the wire it will get deserialized immediately and then put into your process's memory. And I was asking myself, couldn't you actually leverage the borrow of Rust to not deserialize immediately, but borrow from that chunk of memory that you get, and then deserialize lazily, or even use like wrapper pack or wrapper C to not have to do that immediately? and probably you don't need everything from a single struct, or you have a large array or whatever. Did you look into that?
So I think you can't do it really lazily because, especially if you're using tag length value, you can't really see where a struct starts and ends. It's like not a consistent layout. Yeah, you might have two messages which have like the same content but completely different layout, and they're still valid SommIP. So it's a bit difficult. On the borrowing part, that is actually possible to some very limited degree. But for example, yeah, if you want to borrow a string, then it has to be UTF-8 encoded on the wire, and SommIP just says you use whatever string encoding you like. So unfortunately, it doesn't really work most of the time.
Thank you. We have one more question here.
Hi. So something of a high-level question. Do you intend for this to go into production, into series production, or is it a demonstrator?
For now, it is just a demonstrator, to be honest. We still have a long way to go. We plan to have it in mass production somewhere in the future. And I'm kind of confident we can do so, yes.
Okay, great. Thank you so much, Seb, Simon, and Morten for your talk. And
thanks for calling me Seb.
Yes, I take notes. So thank you very much. One more round of applause.